Let's do a little thought experiment. Let's say you have a class of students and they're they're working through a course, and some of the students are proactive and they ask their instructor questions about the course, and some of the students don't. And so it turns out that out of the students who regularly ask questions of their instructor, 60% of them end up getting an A. And out of the students who don't ever contact their instructor or ask them questions, only 10% of them get an A. So, what percentage of the class gets an A? Can you tell? Take a moment and think about that for a second. Well, the question you might be asking yourself now, and this is what we don't know, of course, is how many students in the class ask questions, right? If a lot of students ask questions, then the total number of people who get A ought to be closer to that 60%. On the other hand, if not a lot of students ask questions, then the total number of people getting A will be closer to 10%. And if it's some combination of the two, we expect something in between. So one way to visualize this is, let's say, and follow my cursor here, that X is the event getting an A, and Y is the event asking instructor questions. So if you assume Y, or if you're given Y, the probability of X, what do we say, was 60%? Cool. And not Y then is the event that you don't ask questions, or Y complement, and we say, all right, there's a 10% chance of that. And so what we have then is a sort of partition of the total student population here into two groups. So here we have one group, the students who ask questions. Here with the second group, the students who didn't. In the first group here, 60% of them, right, will get an A, so that's the blue. And over here, only 10% of these students in this column here uh, get an A. And so right now, it defaults to, or this particular calculator, which by the way you can find on my webpage, defaults to 50%. So it's half and half right now. Half asking questions, half not, right? But we weren't given that information. So how many people get an A depends on how many people ask questions. And like we said, if a lot of people ask questions, then almost everyone is in this first column. So the proportion of people uh, that get an A is closer to our 60%. Here we see is 0.54, and what we have the people who asked questions and got an A, and that's 52.8% of the student body. And then we have 1.2% down here of the students who uh, didn't ask questions but still got an A. Now, if not a lot of students ask questions, we can slide that over here, and we can see, all right, uh, that the answer here is closer to 10%, right? We have 0.08 or 8.9% of students here uh, who didn't ask questions and got an A, and then over here, 6.6% of the students did ask questions to get an A. And of course, pay attention to this P of X here. We can be as low as 10%, and that's what happens when no students ask questions at all, and that can climb up all the way up to 60%, and that's if every student in the class asks questions, right? So any value really between 10 and 60 is a possibility here. All right. And so you so when dealing with questions like this, you could be asked a number of questions. So an example of one type of question would be if 30% of the class ask questions, what percentage of the class overall would get an A? And so we can see from that all right, if 30% of the class ask questions, then out of this 30%, which is this column here, 60% of them get an A, and so that's this 18% right here. Then out of the 70%, which is the students who didn't ask questions, 10% of them get an A, so that's a total of 7% down here. So we put these two things together and we get that 25%, right, of the entire class will get an A if 30% of them ask questions regularly. And by the way, you can see also that all of the other information here is calculated, right? So 18% is asked questions and got an A. And 12% here is asked questions and didn't get an A, right? That's the 40% of the 30% here. Here, 7% didn't ask questions and got an A. And then the 63% then is didn't ask questions and didn't get an A. If we put these two together, then 63 and 7, that's 70%, right? That's the total of this column. The 18 and the 12% together form 30%, which is this column, right? So this is 30, this is 70. And this is enough information for us to fill out a Venn diagram, right? And so we can take our two interlocking circles, draw them. We can put the 18% directly in the center and then fill out the rest of those pieces. And once you have a Venn diagram filled out, then you really are able to answer any question about probability, any follow-up questions that may arise, because you now have all of the pieces to the sort of probabilistic situation that's occurring. All right. So let's say instead of being told how many people asked questions, we were told how many people got an A. It's like, all right, half the class got an A. So then, if half the class got an A, how many people asked questions? And this is a little bit more subtle. So let's go ahead and start here. So right off the bat, I know it's not none of the class, because if no one asked questions, then only 10% of people would get an A. All right, and as I increase the number of people who ask questions, I can see that right here, that the proportion of people who get an A goes up and up and up. And at some point that ought to hit 50%, right? Oh, right there. It's 50% at 0.8. Right, so if 80% of the class ask questions, then 60% of the 80% is 48%. Both asked questions and got an A. Then 20% of the class didn't ask questions. 10% of them got an A, so that's a total of 2%. And I put my 48 and 2 together, and that's 50% right there, right? And so there's a nice little tool here where I can set the target for my probability of X that I want to find. And if I click that, it kind of tells me what the Y value should be for that thing. So let's say in a different class, if only 35% of students got an A, then in that class, half the students asked questions and half didn't. And then I can go ahead and slide that back over. And once those are all aligned, right, we get that 35% of them got an A. So this is just to sort of illustrate sort of visually what's going on with Bayes' theorem. And Bayes' theorem itself is a fairly straightforward statement about conditional probabilities. So I'm going to go ahead and look at the handout that I have in D2L. You can also read about this you can also read about this in the textbook as well, but just going to pop over here briefly. So let's first ask ourselves if we believe this statement, that the probability of some event A is the same as the probability of A and B plus the probability of A and not B. So again, it helps to concretize this. Let's say probability of A is it rains, and probability of B is, event B rather, is that I get sick. So event A is it rains, event B is I get sick. So what's the chance that it rains? Well, either it rains and I get sick, or it rains and I don't get sick, right? There's not really a third probability, and there's no overlap between getting sick and not getting sick. So if I take all the days that it's raining and I'm sick, and all the days that it's raining and I'm not sick, and I put them together, that's all the rainy days. So this line here should be believable. It's like, all right, well, so if you believe that the probability of A is the probability of A and B with A and not B, then we can clearly make this replacement here, that the probability of A and B is A given B times the probability of B plus the probability of A given B complement times the probability of B complement. And this just comes from the definition, right? The algebraic definition of A given B and A given B complement. And you can review this in section 2.2. And those division rules, we touched on this in the previous video as well as to why that's true. And then finally, the probability that B doesn't occur is simply 1 minus the probability that B does occur, right? Because what's the chance that something doesn't occur? It's take the whole probability space, take out B occurring, what you have left is B not occurring. And so we have an equation here, P of A is P of A given B times P of B times P of A given B complement times 1 minus P of B complement. And once again, this is an equation with 4 unknowns. So if you can fill in 3 of those things, then you can automatically solve for the 4th. So, for example, if, let's change up again, let's say B is the event that you, that you use drugs, say, because this is related to one of our homework problems. And let's say A is the probability that you test positive for that drug. Now, if you use drugs, there's going to be some chance that you test positive for it. And unfortunately, even if you don't use drugs, there's some chance you test positive for it because these tests are not 100%. And so, how many people test positive? It's going to be the chance of you testing positive, given that you use drugs, times the percentage of people who use drugs, plus the chance you test positive without using drugs, times 1 minus the proportion of people who do use drugs, i.e. the people who don't use drugs, right? So if you were told how many people use drugs, you can figure out how many people test positive, and if you knew how many people tested positive, you could solve for P of B, the probability that you use drugs. And in that case, it's just a matter of solving a linear equation. All right, well, I hope that helps, and I'll talk a bit in the next video about expectation and standard deviation and variance of random variables and linear combinations of random variables. And if anyone wants to see like a problem worked out from the homework and or maybe at least talked about in some more detail, please let me know. I can record a video about that as well.